Welcome back to Neural Intel.
Great to be diving deep again.
Today we're tackling a really fascinating area within multimodal AI, making these powerful models, well, smaller and more efficient.
That's right. Our main source today is a research paper called SmolVLM, Redefining Small and Efficient Multimodal Models. It's from researchers at Hugging Face and Stanford University.
Exactly. And this paper gets into the technical nuts and bolts behind a new family of compact vision language models. So for you, our listener, who wants to really grasp the key technical steps forward without getting bogged down in excessive detail, this deep dive is for you. We're extracting the core technical insights.
We'll look at how SmolVLM gets impressive results using way fewer resources. So we'll unpack their architecture, their tokenization methods, training strategies, the works.
And just a reminder, we focus purely on the technical aspects and implications here on Neural Intel. For links to the papers we discuss, like SmolVLM, and to stay updated, do check out our webpage. The link is right there in the bio.
Definitely. We're looking at how researchers are getting around the challenge of putting advanced AI onto devices that just don't have much compute power. And this paper has some really compelling ideas.
Okay, let's get into it then, because usually when we talk vision language models, VLMs, we think big, right? Massive compute needed, huge demands.
Absolutely.
So what's the real technical driver here? Why the push for smaller, more efficient versions?
Well, the bottom line is practicality. These large VLMs, they show incredible capability, sure, but their size makes them really hard to actually use in a lot of places.
Like on your phone or edge devices.
Exactly. Mobile phones, embedded systems, and you can't just, scale down a huge model proportionally and expect it to work well with much less power.
Doesn't work like that.
No, it needs a fundamental rethink of the model's design, really.
Right. So it's not just about making things convenient. It's about opening up totally new technical possibilities, new applications. Okay, so enter SmolVLM. What's its core goal?
SmolVLM is basically a series of these compact multimodal models. They're engineered from the ground up specifically for efficient inference.
Inference being the stage where the model actually makes predictions or generates output.
Correct. The researchers really focused on optimizing every single part of the pipeline. The architecture itself, how images and text get turned into tokens the model understands, the training process, all aimed at slashing resource use, but crucially, without totally tanking the performance.
And the results look pretty promising on that front. What are some of the standout achievements they report?
Oh, definitely. Their smallest version, the SmolVLM 256M, it runs using less than a single gigabyte of GPU memory during inference.
Less than a gigabyte. That's tiny for a VLM.
It is, and what's technically really interesting is that this tiny model actually manages to outperform IDFix ADB.
Which is much bigger.
Much, much bigger, about 300 times larger in parameter count. So that really underscores the power of smart, efficient design.
Wow. Okay, less than 1 GB, beating something 300 times its size. That is a serious jump in efficiency. And it's not just the smallest one that's impressive.
No, not at all. They have a larger, well, relatively larger 2.2 billion parameter model. And that one rivals current state-of-the-art VLMs.
But uses less memory.
Exactly. Requires only about half the GPU memory compared to some others with similar performance. So you're getting comparable results with much less demanding hardware.
That's a big deal for deployment.
Huge. And another key point, SmolVLM isn't limited to just static images. It handles video comprehension too, which broadens its potential uses quite a bit.
Okay, so the big question, how did they do it? Technically speaking, what are the core architectural trips or innovations they use to get this efficiency?
All right, let's dig into the architecture. Figure 2 in the paper lays it out. It starts with the input, an image or a video. First step is splitting it up.
Breaking it into smaller pieces.
Sort of, yeah. Manageable segments. Then these segments get encoded into numerical representations, visual features. But a really key innovation happens next, something called the pixel shuffle operation.
Pixel shuffle. Okay, now that sounds interesting. Explain that. What's the technical idea there?
Sure. Pixel shuffle, and you can see it illustrated in their figure 4, is a pretty clever way to rearrange those encoded visual features.
Rearrange how?
Think of it like this. You take a higher resolution image map, represented by many small bits of data, and you reorganize it. You end up with a lower resolution map, spatially speaking, but each point in that map now holds more information. The channel depth increases.
Okay, so you trade spatial detail for channel depth.
Essentially, yes. And the big benefit, it drastically cuts down the total number of these visual tokens that the language model part has to actually look at and process.
Fewer tokens,
Yeah.
meaning less computation needed later on. I get it. It's a compression technique
Yeah,
almost.
exactly. It compresses the visual information into a format that's, let's say, more digestible for the subsequent language model.
Makes sense. So after this pixel shuffling, what happens to these rearranged visual features?
They get projected. Basically, they're mathematically transformed so they exist in the same space as the text embeddings.
Turning them into something the language model can understand, like visual words.
That's a good way to put it. Visual tokens. This is usually done with a fairly simple neural network layer. Then these visual tokens get combined with the tokens representing the text input.
How are they combined? Just stuck together?
They can be put sequentially or sometimes interleaved, depending on the specific setup. But the point is, they're merged before being fed into the main language processing engine of the model.
Right, so the model sees the text and the visual information together, unified. Okay. Now, the paper highlights several specific findings from their experiments. Let's tackle finding one. It's about parameter allocation.
Yeah, this one's quite insightful. For these compact models, it turns out that how you divide up the model's capacity, its parameters, between the part that processes vision, the encoder, and the part that processes language, the LM, that balance is critical.
What did they find specifically?
They ran experiments pairing different sizes of their compact language model, SmolLM2, with different sizes of a vision encoder called SIGLAP. And the key result, which you can see in their figure 3 left, was kind of counterintuitive. Using a really big, powerful vision encoder with a small language model actually hurt the overall performance.
So more power in the vision part wasn't always better. You can't just strap a giant engine onto a small car, so to speak.
Precisely. It seems the smaller language models actually do better when paired with a vision encoder that's also relatively compact and efficient.
Interesting. Why would that be?
The thinking is that the language model needs enough capacity itself to actually make good use of the potentially richer information coming from a bigger vision encoder. If the LM is too small, it just gets overwhelmed or can't leverage the detail effectively.
So a balanced design is key for these resource-constrained models. That's a super valuable technical point for developers. What about finding two? Extended context length.
Right, another crucial optimization. They found that giving SmolVLM the ability to handle longer sequences of tokens, a longer context window, provides a significant performance boost.
Why is that particularly important for visual language models?
Well, think about it. Even a single high-res image, once it's broken down and tokenized, especially after something like pixel shuffle, can still generate a fair number of visual tokens. To process these effectively, especially if you have multiple images or video frames, you need that capacity. So they push the context window out. For the 2.2 model, it's 16,000 tokens.
16,000. That's quite large. And for the smaller ones?
Still substantial 8,000 tokens for the smaller variants.
Okay, how did they technically manage to extend it? Doesn't that usually make things computationally heavier?
They primarily did it by tweaking a specific setting in their positional embedding method. They increased something called the ROPE base.
ROPE, rotary position embeddings.
That's the one. It's a way models keep track of where each token is in the sequence. By adjusting this ROPE base, drawing on some recent techniques, they could effectively handle longer sequences without a massive computational hit.
Clever. And they fine-tuned it carefully.
Yes, they fine-tuned on a mix of long and short context data. This helped ensure the model stayed stable and performed well regardless of the input length. Figure 3 middle shows this worked well.
Smart way to boost capability. Okay, finding 3 brings us back to pixel shuffle, but focuses on how much compression.
Yeah, exactly. They found that for these small VLMs, it's actually beneficial to be more aggressive with the pixel shuffle compression than you might be for a larger model.
More aggressive how?
So while some models might use a shuffle ratio of 2, effectively reducing token count by 4 times, 2 by 2, small VLM uses a ratio R of 4.
Which means 16 times reduction.
4 by 4.
Correct. A 16-fold reduction in the number of visual tokens.
Wow. Doesn't that risk losing a lot of important visual detail, throwing out too much information? You'd think so, perhaps. But their experiments, shown in Figure 3, right, suggest otherwise for these smaller models. The massive reduction in tokens dramatically lessens the computational load, especially for the attention mechanism in the language model part.
The attention mechanism, that can be computationally expensive.
Very. So, while maybe some very fine-grained spatial detail might be slightly less precise, the overall performance across different tasks actually improved, likely because the model can now handle longer visual sequences more efficiently within its limited budget.
Okay, so it's a trade-off. Less fine detail, maybe, but better ability to process the bigger picture or longer sequences. Interesting. Let's move to finding 4, efficient encoding for images versus videos.
Right, here they noticed that the best approach wasn't the same for still images and for videos.
How so?
For images, they found that splitting a high-resolution image into multiple smaller patches alongside a downsized version of the whole image actually helped performance on vision tasks.
Why would splitting it help?
The idea is it might allow the model to focus its attention more effectively on different regions or aspects of the image, like breaking down a complex scene.
Okay. And what about video? What did they find there?
For video, a common technique is to average the features across several frames to get a single representation. But they found this actually hurt performance for SmolVLM. You can see that in figure 3, right, as well.
Hurt performance. Why?
Their guess is that averaging frames essentially blurs out the crucial temporal information that changes happening over time. And that's vital for understanding video content, obviously.
Yeah, motion change. Averaging would lose that. So what do they do instead for video?
They simply rescale individual video frames to the resolution the image encoder expects, rather than averaging them, preserves that frame-by-frame information.
Makes total sense.
Yeah.
Okay, that covers the architectural findings. The paper then moves into small instruction tuning. What were the key technical discoveries there? Finding 5 first.
Finding 5 is about how the model learns to understand the spatial layout of visual tokens, like where different image patches came from. They tried 2 methods, using simple text strings like coordinates versus using special learned positional tokens.
What happened?
With these simple string tokens, especially in the smaller models, they ran into trouble. They called it the OCR loss plague.
OCR loss plague. Sounds dramatic. What does that mean?
It means the training loss seemed to be going down, suggesting the model was learning, but its actual ability to perform tasks needing spatial understanding, like reading text in images, OCR, wasn't improving. It plateaued. Figure 5 left shows this.
A tricky training problem. How did the learned positional tokens fix it?
By using dedicated learnable embeddings, basically, unique numerical codes to represent the position of each visual token, they saw much better training stability and convergence. And importantly, it led to significantly better OCR accuracy and just a better general grasp of spatial relationships. Figure 5, center and right, really highlights this improvement.
So instead of literal text coordinates, the model learned a more abstract, effective way to represent where things are. Neat. Okay, finding 6, structured prompts and media segmentation.
This one highlights how important it is to give the model clear, structured input during training. They found that adding system prompts short instructions at the start, like analyze this image, gave a noticeable performance boost.
Especially for image tasks.
Particularly for image tasks, yes. And they also added special marker tokens around the image or video data.
Like what?
Things like, this is an image before the visual tokens and maybe an end image marker after, or similar for video. This seemed to help the model, especially with video, distinguish the visual input clearly. Figure 6 illustrates the setup.
Like signposts for the model.
Exactly. They also did something called user prompt masking during fine-tuning, which helps prevent the model just memorizing specific question phrasings and makes it generalize better.
Good practices for robust training. Now, finding 7 looks at reusing text data. This sounds like it should help.
You'd think so. They tried adding text data used for fine-tuning large language models, high-quality conversational text, into their multimodal training mix. They called this data Smalltalk.
Expecting it to boost the language side.
Right. But surprisingly, as Figure 7 left shows, it actually degraded performance in these smaller multimodal models. They saw performance drops on both image and video tasks.
Degraded. Why would adding good text data make things worse?
Their hypothesis is about data diversity. Adding this specific type of text data might have inadvertently reduced the overall variety in the training set, kind of skewing it. And for these compact models, that loss of diversity apparently outweighed the benefit of the quality text.
Wow. So data diversity is really key, even over perceived data quality sometimes. Okay. Finding 8. Chain of thought reasoning. CUT-TT.
Yeah, chain of thought prompting helps large models reason step by step. So they tested adding CUT data to SmolVLM's training.
And for small models.
Turns out, less is more. They found that using too much CUT data actually harmed performance significantly, especially on image tasks. Figure 7, middle, shows this quite clearly.
Really? Why would reasoning data hurt?
It seems these smaller models have a limited capacity. Flooding them with complex, text-heavy reasoning examples might interfere with their ability to process the visual information effectively. A tiny amount of cut data, like 0.02%, gave a slight boost, but anything more was detrimental.
Fascinating. So you have to be really careful tuning the data mix for smaller models. Finally, finding 9 video sequence length.
Here they looked at the average duration of video clips used in training. They tried different lengths, from about 1.5 minutes up to 3.5 minutes.
Any effect?
As Figure 7 shows, increasing the duration up to around 3.5 minutes generally improved performance on both video and image benchmarks.
Why would longer videos help image tasks too?
It probably helps the model learn better associations between visual patterns and language across longer timescales, which might generalize. But pushing beyond 3.5 minutes didn't give much extra benefit compared to the increased compute cost of processing longer videos.
So a sweet spot around 3.5 minutes for training video length in their setup.
Okay. So based on all these findings, they developed 3 specific SmolVLM models.
That's right, 3 variants targeting different levels of resource constraints. There's SmolVLM 256M, the tiny one needing less than 1 GB RAM, ideal for really tight edge devices.
Okay.
Then SmolVLM 500M, kind of the mid-range option, balancing efficiency and performance for slightly more capable edge hardware.
And the largest.
That's SmolVLM 2.2B, still compact compared to giants, but aiming for higher performance on more powerful edge systems. Needs around 4.9 gigabytes of RAM, roughly.
Got it. 256M, 500M at 2.2B. How do they stack up against other models of similar size in benchmark tests? The results, which are in Table 1 and visualized nicely in Figure 1, are technically very strong. Despite being small and frugal with memory, they perform really well across standard vision language and video benchmarks.
Any specific examples?
Well, the 2.2B model does great on tough benchmarks like MathVista and ScienceQA. And it often outperforms models that need significantly more memory, like MALMO-E A1B7B or Qwen2VL-B.
Outperforming bigger models.
In some cases, yes, or achieving very comparable performance with much lower resource needs. They also show strong results on video tests like Video MME and WorldSense.
That's seriously impressive, punching above their weight class, you could say.
Right.
What about actually running them on devices? Did they test the practical speed?
They did. Figure 9 shows on-device performance metrics. They measured throughput tokens generated per second on typical GPUs like NVIDIA's A100 and L4, showing the speed benefits of the smaller sizes.
And the most interesting part.
For me, it was demonstrating the 256M model running inside a web browser using WebGPU.
In a browser. Seriously.
Yep. On a standard MacBook Pro, they got a usable generation speed. That really opens up possibilities for accessibility.
Now, running a VLM in your browser, that lowers the barrier significantly, and people are already building things with this.
It seems so. The paper mentions a few downstream applications. Call SmolVLM for efficient on-device inference in browsers and mobile apps, SmolDockling, an even tinier version for document processing,
Documents make sense. What else?
and BioVQA, using SmolVLM for biomedical visual question answering. Imagine helping doctors interpret medical images, maybe in places with limited resources.
Okay, let's try to synthesize this. What does this SmolVLM research really mean for you, the listener, interested in AI?
I think the big message is that state-of-the-art multimodal AI isn't always about building the absolute biggest model possible. These technical innovations in architecture, tokenization, training show a path to powerful AI that's much more deployable.
Right. And here's where it gets really exciting from a technical application viewpoint.
Yeah.
Think about having sophisticated vision and language understanding running locally, right on your phone, or other edge devices.
Exactly. That could unlock so much. Real-time accessibility tools, smarter robots that perceive and interact, truly personalized assistance, all without constantly relying on the cloud.
So this deep dive into SmolVLM gives you a solid technical picture of how these efficient models are being built. We've seen the specific design choices and training tweaks that lead to big performance gains with tiny memory footprints.
And looking ahead, what does this suggest about AI development? Probably a trend towards more specialized, resource-aware models designed for particular hardware targets.
Instead of just scaling up parameters indefinitely.
Precisely. Which could, in turn, make advanced AI much more accessible, running on a wider range of devices, democratizing it in a sense.
Okay, so for a final provocative thought to leave you with, how might these strides in efficient, multimodal AI change the whole cloud versus edge computing balance in the next few years?
Yeah, what new user experiences become possible when genuinely powerful AI can live comfortably on even the smallest, most resource-limited devices?
This SmolVLM research definitely gives us a fascinating glimpse into that potential future. A lot to think about there.